In this video, we are going to cover how to draw Lewis structures. And Lewis structures can kind of be fun to draw because they don't involve a whole bunch of math, which is a little bit different in chemistry. So I'm going to go through the rules. We are going to stop right before formal charge. We'll worry about that another day. So all of these things with formal charge and rules 5 and 6, we will worry about another time. So we are just worried about rules 1 through 4. So you need to have your periodic table handy because your periodic table will tell you your valence electrons. So rule number 1 when drawing Lewis structures is that we will count all the valence electrons in your compound. Do not forget to take into account the charge of your compound, and we will write this number down. This doesn't seem important yet, but it will be. It'll be that compounds with charges will be drawn in brackets. We are going to connect all of the atoms together with bonds. A bond is represented by a line. So if we have a carbon-oxygen bond, it would look like this. And a bond represents 2 electrons. Okay. The atom that can form the most bonds will be the one that goes in the middle. And typically this one will be the unique atom, okay? So for example, if we had perchlorate, which is ClO4 minus 1, we have 1 chlorine and 4 oxygens. So we would call chlorine our unique atom because there's only one of them, and that one would go in the middle. And we'll see how this works in just a second. Now, hydrogen never forms more than one bond, so, and we're going to see this, but hydrogen is never going to be our central atom. We're going to add lone pairs to each atom to give it 8 electrons. Hydrogen does not get 8 electrons. We'll see that hydrogen has a lot of exceptions. Boron and aluminum typically only form 3 bonds, and beryllium typically forms 2 bonds. Okay? Do not forget an octet on your central atom. Now here's the part that we're going to have to work on, is that if you end up with too many electrons, then we will remove 2 lone pairs and insert a multiple bond until your count matches the correct number of valence electrons that you added up in step 1. And if your count is too few, then we're going to add a pair of electrons to your central atom. If our count is too many by 1 electron, then we would take 1 electron away from the least electronegative atom. Okay, this is rare. We're not going to see this. So as far as honors chemistry is concerned, 4C is not something that I'm worried about. Okay, if you move on to AP chemistry or organic chemistry, we'll see that, but just not in honors chemistry. Okay, so let's do some practice problems. Have your periodic table ready, and here's how we're going to count our valence electrons. We're going to find nitrogen on the periodic table, and if you find where nitrogen is, you'll notice that it is in family 5A. So nitrogen has 5 valence electrons. Oxygen is in family 6A. It's right next to nitrogen, and it has 6 valence electrons. But there's 2 oxygens. So we would take 5 plus 12, and we might say 17. But you may notice that we have a -1 charge. That means we have an extra electron, so we'll add 1 more electron, and when we take 5 plus 12, we get 17 plus 1, we get 18 valence electrons. We should be expecting an even number of valence electrons every single time. Now, our unique atom is going to be nitrogen here, and let me explain something about nitrogen. Nitrogen is in family 5A. Oxygen is in family 6A on the periodic table. There is a rule that maybe you've heard about, whether it be in biology or maybe in middle school science, that says atoms tend to prefer to have 8 valence electrons. This is called the octet rule. So nitrogen, to get to 8 valence electrons, it tends to form 3 bonds, where oxygen, to get to 8 valence electrons, tends to form 2 bonds. Okay, so notice 5 plus 3 will give us 8. 6 plus 2 also gives us 8. And so because of that, we can say that nitrogen tends to form more bonds. If we go back up to our rule, we said in, let me use a different color, rule 2, that the atom that can form the most bonds tends to go in the middle. And so here, this would be nitrogen. Now, most of the time it's going to be easy to see that nitrogen is our unique atom, and so it will go in the middle. So we're going to put a nitrogen in the middle, and I'm going to bond it to oxygen. Okay, so I'm going to do something that looks like this. A bond has 2 electrons, and so maybe it's helpful to draw little dots at the end there for you to see the 2 electrons that are making up that bond. Okay, we've counted our valence electrons, we've put nitrogen in the middle, and we've bonded our terminal atoms or our oxygens to our nitrogens. Now we're going to give everything 8 valence electrons. What I want you to think about is we have, nitrogen. We're going to cover all 4 sides with either a lone pair, which this would be a lone pair. So we could get something that looks like this, cover all 4 sides with lone pairs. We could do 3 lone pairs in a bond. We could do 2 lone pairs in a bond. We could even do 3 lone pairs in a bond. We could even do 4 lone pairs, 4 bonds and no lone pairs. So we want all 4 sides of our atom covered. So what I'm going to do is I'm going to put these dots around. And I've gotten all 4 sides of my atoms filled either with a bond or a lone pair. Now, let's count how many electrons we have, and I say to count by 2s. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 electrons, and we counted originally, we need 18. So 20 is no good. So we'll go back up to our rules, and this happens a lot. If our count is too many, then remove 2 lone pairs and insert a multiple bond between the 2 atoms. So how this works is we will find our central atom, we'll erase a lone pair, and then pick any of the terminal atoms. So you can pick left oxygen or right oxygen. We'll remove a lone pair, so I picked the left oxygen, and we'll insert a multiple bond. The net loss when we do something like that is 2, and I will show you that when we count now, 2, 4, 6, 8, 10, 12, 14, 16, 18, now we have 18 valence electrons. This is a good Lewis structure. And actually, I'm going to get rid of my yellow here. So 18 is good for us. Now, we're almost done. In other chemistry classes, you will see teachers use big brackets like this to indicate that your ion or that your Lewis structure is an ion and has a charge. So they might do something that looks like that. I think those big brackets are kind of bulky, so I always just do a little bracket and put something like that. Okay, so that is nitrite's Lewis structure. Okay, let's do a few more. I'm going to just get this one out of the way. Let me just get rid of this. Okay, now we're going to count our valence electrons. We have 2 nitrogens. Each nitrogen has 5 valence electrons plus an oxygen. So we get 2 times 5 is 10 plus 6 is 16 valence electrons. We've already decided that between nitrogen and oxygen, nitrogen can form the most bonds, so nitrogen will go in the middle. So we'll put a nitrogen in the middle, we'll put an oxygen on one side, and a nitrogen on the other side. It does not matter if you also had O in like this, okay? So either is fine. We're going to go ahead and give everything 8 valence electrons, or cover each side with either a bond or a lone pair. And now we're going to count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 is not a good number for us. So what we're going to do is we'll erase a pair from the central atom and then pick any terminal atom and erase a pair and add a multiple bond between them. Now we'll count again. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 valence electrons is still no good. So we'll do this again. Erase a pair, add a multiple bond. And then we'll count 2, 4, 6, 8, 10, 12, 14, 16. Now we get 16, and this is our Lewis structure. There is no bracket because we have no charge. Now, you may be wondering, could we have had a triple bond like this, because I chose to go with my nitrogen on the left each time I created a multiple bond. So this works. Or we could have done just 2 double bonds. Okay, so any of those would have been acceptable answers on a test or quiz. Okay, a good one here, and I'm going to do a lot of these examples, so don't worry so much about if it doesn't make sense just yet. You'll get the hang of this. Let's get our valence count. Carbon has 4 valence electrons. It's in family 4A. Hydrogen has 1. It's in family 1A, so 3 times 1. And then fluorine has 7 valence electrons. We add that up, and we get 14 valence electrons. Now, most of the time, your unique atom can go in the middle, but here we have 2 unique atoms. We have carbon and fluorine. So here's what we're going to need to do, is we need to think about if carbon has 4 valence electrons, ask yourself, how many bonds is carbon going to tend to form? Well, the octet rule says it wants 8, so it's 4 away, so it'll form 4 bonds. Fluorine, on the other hand, has 7 valence electrons. To get to 8, it would only need to form 1 bond. So the one that forms the most bonds tends to go in the middle, so we'll put carbon in the middle, and then we're just going to put our 3 hydrogens on this and a fluorine. Okay, now we're going to give everything 8 valence electrons, so cover each of the 4 sides, and this is the first time we're seeing hydrogen. If I go back up to our rules, we said hydrogen does not get 8 electrons. Okay, hydrogen is in the first energy level, and if we think about hydrogen, it could only ever be 1s2. Okay, so hydrogen actually only ever gets 1 bond and no lone pairs. So that follows our rule so far. Now we're going to count 2, 4, 6, 8, 10, 12, 14. Here we have 14 valence electrons. We don't need to do any more. That is what CH3F looks like. Okay, I'm going to skip 4 for right now just because I'm running out of room. Let's do 5. We have arsenic. Arsenic is in family 5A, so it has 5 valence electrons. We have 5 fluorines. Each fluorine has 7 valence electrons, so we get 35 plus 5. We get 40 valence electrons here. Arsenic is our unique atom, so it will go in the middle, and I will put fluorine around. There's 5 of them, so I'm going to do 4. And then on that 5th one, just squeeze it in somewhere, and we get something that looks like this. Give everything 8 valence electrons, so one, cover all of the 4 sides of our F. Notice that arsenic already has all 4 sides covered and more, so we don't need to add anything to arsenic. Okay. So now we're going to count and see if we got 40. If we didn't, we can make adjustments by adding multiple bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. We got 40. This is a good Lewis structure. Okay, so sometimes it works out. Let's look at SO3 versus SO3 2-. This is sulfur trioxide. And then this is sulfite. One of the differences I know is that sulfite has a charge, so it will go in brackets at the end, but we're not just there yet. So let me do SO3. Sulfur has 6 valence electrons. It's in family 6A. Oxygen also has 6 valence electrons. It's in family 6A, and we add that up. We get 24 valence electrons. Sulfur will go in the middle. It's our unique atom. We will bond 3 oxygens to it, like so. Now we're going to give everything 8 valence electrons, or cover all 4 sides with either a bond or a lone pair. So we get something that looks like this. Don't forget that we also need to cover all 4 sides of our S. Now we're going to count. We need 24. Let's see how many we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We've got too many electrons. 26 is not a good number for us. So, easy fix. We'll erase a pair from our central atom. Pick any of the oxygens. I'll just pick the right oxygen and pick any of the lone pairs on it. Erase a pair, add a multiple bond between them. Now when we count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, we get 24, and that is what we need. So this is sulfur trioxide. Let's compare that to sulfite. Sulfite is 24 valence electrons from the sulfur trioxide, and then plus 2 from the minus 2, so we get 26 valence electrons. Put sulfur in the middle, bond 3 oxygens here. Give everything 8 valence electrons, including our central sulfur. We count. I did get 26 valence electrons, so we don't need to make any changes. It's very easy on a test or quiz to keep moving, but don't forget to put a -2 there. I am going to show you sulfate here, SO4 2-. So pause the video, try sulfate on your own, and then when you unpause it, I will have it drawn here for you. That is sulfate. No need to change. When we give everything 8 valence electrons, it's at 32, and that's how many we needed, so there's no need to make any changes. Okay, I want to show you some different kind of ones. Okay, let's look at number 10. We have xenon. Xenon has 8 valence electrons, and xenon does not bond under normal circumstances. So you may be wondering, that's a noble gas, that shouldn't be bonding. And just, I agree, it would be under weird circumstances that it would be bonding. Plus 2 times 7, so we get 14 plus 8, what will that be? 22 valence electrons. Xenon is our unique atom. We'll put it in the middle, and we'll bond 2 F's to it. Give everything 8 valence electrons. And when we count, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now this is the first time we're seeing where we're short. We don't have enough. Typically we have too many. So here's our easy fix. I always like when this happens because it's not very hard of what to do. If you're short, all you do is just add however many valence electrons you need to your central element. So we need 2 more. We'll just squeeze them there on xenon. Now we're up to 22, and we are good. That is xenon difluoride. Okay, let's look at 12. Carbon has 4 valence electrons. There's 2 carbons. Then there's 4 hydrogens, and each hydrogen has 1 valence electron. So that would be what, 12 valence electrons? So carbon can form the most bonds here. Carbon can form 4 bonds. So carbon's going to go in the middle, but we don't just have 1 carbon, we have 2 carbons. So here's what we're going to do, is we're just going to bond them together. And then if you continue on with chemistry, you'll learn that a lot of things in nature have symmetry. So this will be a very symmetric looking compound. We have 4 hydrogens, so we'll give 2 hydrogens to each carbon. We'll do something that looks like this. Or actually, it might even make it a little bit cleaner if we did it like this. It doesn't matter. You could have kept it how I had it. That just allows for me to cover all 4 sides of carbon and have those lone pairs there. Hydrogen does not get lone pairs. Now we're going to count 2, 4, 6, 8, 10, 12, 14. We have too many valence electrons, so we'll erase a pair, and add a double bond between, oops, did not get that second one erased. Add a double bond between the 2. Now when we count, we get 2, 4, 6, 8, 10, 12. We are good. That is C2H4. Okay, so if you have questions on these, please let me know. There is a quiz on Schoology. And if you made it to this point in the video, just send me a Schoology message to let me know that you made it to this point in the video. Just say, Mr. Payne, I made it to this point in the video, and I will award bonus points. Have a wonderful day. If you have questions, please do not hesitate to just let me know, but try out that practice quiz on Schoology. It's a little bit of a different type of quiz. I would, and I said this in the directions, but I would draw your Lewis structures. I think there's 7 of them. Draw them on a piece of paper, and then draw them on Schoology, because I don't think there's a back button on Schoology. So you just have to draw it perfectly the first time. And since we're, erasing double or erasing lone pairs, you might get frustrated if you just try to do it on Schoology. So do it on a separate sheet of paper. But besides that, have a wonderful day.